vary from 45 to, this is not a very special angle because tangent function is equal to 2, right? Tangent function is the y divided by x is equal to 2. You have a smaller angle and upper angle, but you have to have a fixed shortest distance and a fixed longest distance, right? So if this ray is varying from 45 to the largest angle, the distance is not fixed between two numbers. This is not a rectangle. It is R simple region, in fact. Are you convinced it is R simple region? I only want you to be convinced it is R simple region. I don't want you to be able, well, if you can, that's best, but I don't require you to be able to describe it in R simple region. But you have to be convinced it is indeed R simple region. R simple region means if I vary this ray, so say if I have an arbitrary ray between these two angles, if I have a ray between these two angles, the distance is bounded between a value depending on the angle and the other value depending on the angle. All right? It is indeed depending on these two values. As you are changing this angle, these two values are also changing. Now with me? These two values are also changing depending on these two angles, these two formulas. But how it is changing, that is not known. All right? I know this distance, shortest distance, is going to be changing if I vary the angle. This longest distance will also change. So these two radii are changing with respect to the angle. But to describe it mathematically, it's not easy to. Okay? So I want to do a change variable because it leaves me no option. So in order to change variables for the x, y to u and v, you have to design it cleverly. All right? So one of the variables should be pretty clear to you here. I want to choose u to be equal to x times y. All right? So if u is equal to x times y, then I know u will be bounded between 3 and 1. I immediately simplify these two significantly from two hyperbolas to two numbers. Right, that's a big simplification. In order to introduce the other variable v, I have to look at these two equations. What do you want to introduce? So y is equal to 1, x, you have a slope 1, you have slope 2, so you sort of want to introduce a new variable to denote the slope, right? Sort of want to design v to denote the slope. The slope is actually y divided by x. So this equation is equivalent of saying y divided by x is equal to 1. And this equation is y divided by x is equal to 2. So I just modify these two equations slightly, and that becomes clear. V has to be y divided by x. So v will be bounded between 2 and 1. All right? Again, the reason I'm choosing u and v in this way because I can simplify these boundary defining functions from hyperbolas and straight lines to 4 numbers. That is big significant simplification. Wouldn't you agree with me? Right? So if we have so much experience in dealing with integrals, triple integral, double integrals, having numbers as your boundary is much more easier, right, than having functions as your boundary. So now I can easily write down it from 1 to 2, from 1 to 3. The function, integrating function is x times y, and this new variable is just u. So u, then partial xy, partial uv, du dv. So the only thing missing here is I have to see what this Jacobian factor is. Okay, what this Jacobian factor is. So this Jacobian factor, again, I have to change the equations from uv to xy. So I have done this for all the questions, which means you need to solve this pair of equations. U is equal to xy, v is equal to y divided by x. So what is x? In order to get x, I can divide these two equations. All right? I can divide these equations. I have x squared is equal to u divided by v. So x is equal to u divided by v. The reason I'm taking the positive square root is because this is in the first quarter. And v is equal to, sorry, y is equal to, if I multiply these two equations, I'm going to cancel x. So y squared is equal to uv. All right. So m1, 2. If you not see this clearly, 1 divided 2, we're going to get u divided by v is equal to x squared. So 1 times 2, we're going to get uv is equal to y squared. So y is equal to square root of uv. Okay? Because eventually we have to take derivatives, so maybe rewrite this a little bit. It will be y squared. So y x is equal to u half v to minus 1 half. Y is equal to u to 1 half v to 1 half. So in this way, I can easily compute the partial derivatives. Partial x, partial u, partial x, partial v, partial y, partial u, and partial y, partial v. Okay, so let's do that. So partial derivatives, none of you should feel any intimidated by it. It can be complicated in computation, but in concept, it's definitely very easy. Okay, as long as you're taking derivatives, you should be very happy about it. At least comparing when you are doing with integrals. So partial x, partial u would have 1 half u to minus 1 half v to minus 1 half. Am I right? And partial x, partial v minus 1 half u to 1 half v to minus 3 halves. Right? So partial y, partial u is 1 half u to 1 half minus 1 half and v to 1 half. And partial y, partial v, I have 1 half u to 1 half v to minus 1 half. And then I'm taking the determinant. So the product of these two is going to be 1 quarter. U to minus 1 half cancel. V to minus 1 half, I get a V to minus 1. Right? So minus the product of these two anti-diagonal entries. So it's going to be minus 1 quarter u to 1 half, u to minus 1 half to cancel. V to 1 half and v to minus 1, 3 halves, I have a v to minus 1 again. All right? So in the end, I have 1 half of v to minus 1 half. I'm sorry, v to minus 1. Okay, so that's the Jacobi factor. With me? So it's 1 quarter 1 over v plus 1 quarter 1 over v. I'm getting a 1 half 1 over v. So I plug in here, this is nothing but from 1 to 2, from 1 to 3, u divided by v multiplied by 1 half du dv, which will become very easy to compute, right? So this Jacobian factor is just 1 half multiplied by 1 over v. That's what we have. Questions? So I'm going to leave the following work to you. So this is just a double integral with respect to a very simple function u and v. Okay. So in change of variables, the key step is how you're going to introduce this new pair of numbers, new pair of variables. Why you're choosing these two u and v in this way. The biggest reason in double integral and integral is because you can simplify the domain. Okay, you can simplify the domain. Here, originally the domain is pretty complicated. 2 parabolas and 2 straight lines. The domain is no regular shape. But because I can introduce u and v in this way, I can reinterpret this domain in a cube, or in this case, it's just a rectangle. All right? It's just a rectangle. So that's the biggest reason to choose to use change of variables. Okay? So, any questions? So I want to quickly go over the midterm I'm going to see on Wednesday, and then I have to begin the introduction of new chapter.
Listen,
Mm-hmm.
I just have one question.
Yep.
What method did you use here? Can you just go over that again?
Which one?
To find u over v equals x squared and v times. Just that one right there at the top.
This one?
Yeah.
Okay, so this one is coming from so basically I just need to solve for x and y coming from this system of equations. All right? In order to get the x, I need to divide these two equations. So 1 is divided by 2. So if I divide both sides of these two equations, left side is getting u over v. The right side is xy over y divided by x. So y is going to be cancelled, and that's why I'm ending up with x squared. So basically, this is a xy divided by y divided by x. It's going to be xy times x divided by y. So that's where I get x squared. Okay? Any other questions? So I didn't spend too much time in this kind of solutions, just because as long as I change the problem a little bit, you have to solve a different system equations. You know what I mean? You're going to have to solve a different system equations. Either it is linear, that would be the easiest, or it is slightly more complicated, but still within 1 or 2 steps. Okay?
Usually, so that was the confusing part, because if you want to find u or v, here you did like division and multiplication of the two formulas, but in the previous problem you just did you just added them, subtracted them. So it's like it's just like intuitive that you have to like figure it out.
Yeah, that's a very good question. Usually when you solve system equations, you have basically 2 ways to go. Either you can eliminate or you can substitute. Right? Both of these 2 cases I'm using elimination. Just because the equation representations are different, but still I'm going to the same direction. I want to eliminate one variables so I can solve the other one easily. So if you have linear equations, I'm adding them linearly, combine them together in order to eliminate one of the variables. Here I still want to eliminate x or y. Eliminating x is pretty straightforward. You just need to multiply the 2. Right? But eliminating y is slightly more complicated, but still dividing these 2 will eliminate y. But basically I'm using the same method. Okay? Any other questions? Yeah?
How come when you did your programming for this, you still had a variable left over, but for the previous problem, you just got a number?
A Jacobian is, strictly speaking, function depending on new variables. It can be a function of constant number.
Okay.
Right? So constant number can be a review. That can be regarded as special case.
Okay.
So the numbers, if you're getting numbers, this is nice, but it's not very general. Generally speaking, I'm supposed to get a function. Everything?
Why?
Yeah, because these are all partial derivatives. In the end, I'm supposed to get a function as the determinant of these functions. All right? So eventually, generally speaking, I should have a function in the end. But it's just in some special cases, you're getting easier functions. It's constant. Okay? Any other questions? Okay, so in this chapter, all we did is double and triple intervals. And I will say double interval is absolutely the more fundamental one. If we have the experience, and we did have a lot of experience in computing triple intervals. In most of the triple intervals, what we did is actually to reduce it to a double interval. All right? So double integral is absolutely the most crucial part of all. So in double integrals, you have to be able to identify this region. Okay? And I promise you, all the functions I give you, finding the antiderivative is not going to be challenging. Taking the integrals is not going to be challenging. So really, identify this region is the most important step. Okay, the most important step. And we have several different cases. One is a right angle, where R is equal to X is bounded between A and B, Y is bounded between C and D. This is the easiest case, because as long as you have this right angle as the region, you can take the integral with respect to X first, or Y first. All right, so you can take the integration with respect to either one of the two intervening variables. But usually, depending on the function you're getting, one of the two is easier. Okay, so one of the two is easier. So I give you one example first. Okay. So for instance, I have this integrating function. So x, y, sine y squared dx. So I want to take this integrating region. R is from x is bounded between 1 and 2, y is bounded between 3 and 4, for instance. These are not very essential here. It's just a very generic example. Okay? So if I look at this integrating region, I immediately know this is a rectangle, so I can do either one of these two integrating orders. Am I right? You can do either one of them. But you have to decide which one is even more easier. Which means in this integrating function, I want to regard one as constant and the other one as the variable to find the antiderivative. All right? To find the antiderivative. This guy, if you regard y as the variable, the antiderivative is not easy. All right? X is the constant. Basically, you need to find the antiderivative of y sine y squared. It's still okay, but it's not going to be as easy as x is the variable. If x is a variable, this whole thing is constant. You're just finding the antiderivative of x. It's much easier, all right? So you have to decide which order you want to go, and that depends on which one is easier in terms of the antiderivative. So I want to take integration with respect to x first, and then y. Okay, but usually both of them will work. Okay, so you don't have to scare about this rectangle case, but one of them is probably easier. Okay, so then we have this y simple region and x simple region. We have been doing this for so many times. So y simple region, you need to identify, x simple region, what you need to identify. So for instance, I can give you a question. So from 0 to 1, from y to 2, x squared e to xy dx dy. Okay? For instance, I will ask you to evaluate this double integral. Immediately you know this is a x simple region. So x is bounded by a left function and a right function. Y is bounded between two numbers right here. So this is x simple region. So for any double integral or triple integral you're given, you can begin your evaluation right after this. So you look at this, you identify